Flipped classroom video for Maths AS Unit 1, describing space. Scalar and vector quantities. What's the difference between them? Well, scalar quantities are described by magnitude or size only, whereas vector quantities are described by both magnitude and direction. So we can have a little look at a table which shows the difference. So if we look at distance, that's a scalar. That just says how far something is, but displacement says how far it is and in what direction. Similarly for speed. Speed tells us how fast something's going, velocity tells us how fast it's going and in what direction, and so on. Acceleration is a bit of a problem because we don't have a separate word for the scalar versus the vector, but the context will tell you which you're dealing with. Into sort of physics type stuff, we've got mass, which is a scalar, that's a quantity of a body, whereas weight is the force on that body due to gravity. And then we also have the more general force is a vector. It has a quantity and a direction that is acting in. Temperature is scalar, change of temperature is a vector because it could be going up or down. So that's a direction. And then we have fields, which is a slightly esoteric sort of idea which you will come across. And we've got a couple of little pictures. That's what vectors can be represented as, arrows with a direction clearly, and then the length of it represents the magnitude. And this is an example of a field, in this case a magnetic field. So the magnetic field acts along those lines and has a certain size at each position on them. So, representation of vectors. Now, you will have met vectors as column vectors when looking at things like translations in geometry, and you will have seen them with components in the x and y direction. But the simplest way of representing them is with an arrow, as we've just seen. So, this is the vector A, and notice that the A is in bold, which is commonly used when typing. When writing, we tend to write them by underlining the letter that represents them. And this one is also A. Vectors are not positioned in space unless this is specified. So those vectors are both A. The modulus of a vector, so this is the size of it. Remember, vectors have size and direction. So when we're representing them with arrows, the magnitude or size or modulus is the length of the line that represents it. So this is the vector A again, and that's the length of it. And notice the bolded A becomes an unbolded A, or we can put modulus signs around the name of the vector. The negative of a vector is simply the vector with the same modulus but opposite direction. So in this case it would be represented like that. So you can see that that's an arrow same length as A but pointing the other way. So adding vectors. To add vectors we simply place them head to tail. And then the sum of the two vectors is given by the vector going from the tail of the starting vector to the head of the finishing one. So here we have a representation of adding two vectors A and B, so we can see that we've put the tail of B comes from the head of A, and then the A plus B is from the tail of A, the starting vector, to the arrow or head of B, which is the finishing vector. Now, in fact, it doesn't matter which way round we do that. If we do B and then A, we end up at the same point. So, this tells us that we can do it in either order, and this gives us what's called the vector parallelogram. And what that's telling us is that vector addition is commutative, and commutative means that the order of the objects doesn't matter. So, for example, ordinary addition is also commutative, of course. So 2 plus 3 equals 3 plus 2. There are other operations that you know that aren't commutative, for example subtraction. So 2 take away 3 is not the same as 3 take away 2. Okay, thinking now about vector notation, you've met column vectors before, and as a reminder, 4 minus 3 means 4 units in the x direction and minus 3 in the y direction. And we also have an alternative notation using what are called unit vectors. So the unit vector in the x direction is I, and in the y direction j. And when we're writing them, just like we do with the vectors, the complete vectors we've seen, like a and b before, we underline them. So the vector 4 minus 3 can be written as 4i minus 3j, and that's the bolded version we generally use in typing, and that equals 4i minus 3j with them underlined, which is what we use in writing. So in this vector, the I component is 4i and the j component is minus 3j. And the word component generally represents or is used for one of the directions involved in the vector. If we were to put I and j on a coordinate grid, so if we make I come from the origin or 0, 0, then it's just one unit in the x direction, and similarly for j in the y direction. And in A2 you will meet 3D vectors, three-dimensional vectors, in which case we also have a component k which is in the z direction. Okay, so the four rules: addition, subtraction, multiplication and division, and we can add and subtract vectors given numerically quite straightforwardly. This obviously has to give the same result as the previous adding pictorially using the head to tail method. And the key is that if we understand the components as directions, then we can simply add or subtract each component separately. So, for example, if we had 4 minus 3 plus 2, 1, that would equal 6 minus 2, because for the I component we have 4 plus 2 is 6, and for the j we have minus 3 plus 1 is minus 2. And the alternative way of writing that would be 4i minus 3j plus 2i plus j equals 6i minus 2j. And you'll see why the second vector there is in brackets in a moment. If we're subtracting, it's the same job. We have 4 minus 3 take away 2, 1, so the I component is 4 take away 2, which is 2. And the j component is minus 3 take away 1, which is minus 4. And if we write them in component form, you can see why it's important to make sure you put brackets, because we now want to make sure that that j in the 2i plus j is indeed subtracted, whereas without the brackets that would be easy to, well, it wouldn't actually say that. So we've still got the same sum going on. So having a look at what this looks like, if we use the sum that we've just considered, then this is what we have. So A is 4 minus 3, and we can see roughly anyway that we've gone across 4 and down 3, which would fit in with an ordinary coordinate grid. B is 2, 1, so 2 across and 1 up, and we can see that that's happened. And we've got A and B head to tail. That gives us A plus B, and we want that to be 6 across and 2 down for the minus 2, and indeed that's what it looks like. For A minus B, we've done A and then we've added minus B on, which is the same as subtracting B. So that gives us our A minus B, and indeed that does look right in that we want it to be 2 across and 4 down. Notice that B is written twice because we're still dealing with vectors that aren't fixed. The B towards the bottom is fixed because that's involved in the addition, so we're putting the tail of that to the head of A to do the addition, but in general it's not fixed. And I've already mentioned, but notice that A take away B is the same as A plus minus B, which is the same in ordinary addition or subtraction, and it works for vectors too. So the power of vectors is in generalization and other things, but generalization is certainly one of the benefits of vectors, and that means they give generalizable results. So if we look at the pictorial representation of a plus b that we've just seen, then we can see the addition subtraction diagram from the previous slide, but we'll just have a look at a couple of others. Just have a look at these, perhaps pause the video for a moment and see what you notice about them. That's perhaps something you could discuss with your teacher. Okay, moving on to multiplication and division, and this isn't so simple. So we can't multiply vectors in the same way as we add numbers, because what would we multiply? There are in fact ways that we sort of multiply vectors, in that we have something called the scalar product and something called the vector product, which you may meet later on in your studies. But in terms of an equivalent to ordinary numerical multiplication, what we have to do is simply multiply or divide them by scalars. What we do when we're dealing with component represented vectors is we multiply each component by the multiplier, or we divide each component by the divisor. So, for example, if we had 3 times minus 2, 3, then the I component would then become 3 times minus 2, so minus 6, and the j component 3 times 3, so 9. And if we write it in component form, it looks like this. For division, if we started with minus 2, 3 divided by 3, then the I component would be minus 2 divided by 3, which is minus 2/3, and the j component would be 3 divided by 3, which is 1. And again, we can write that in ij form. So what does it look like? Well, this time a is minus 2, 3, and if we multiply it by 3, we can see that we have a there in red and 3a, and what we notice is that the direction is unchanged, but the vector is stretched by a factor of 3 in this case. And if we divide by 3, then the original vector there is in red and the vector a divided by 3 is in green, and we can see that again the direction is unchanged, but the vector is contracted instead of stretched. And notice when multiplying by a scalar, we always obtain a parallel vector. Now I've drawn these vectors sort of superimposed so that you can compare them, but of course they could be freestanding, as it were. The 3a could be drawn elsewhere and it would still in that case be parallel. And in fact, we can look at that the other way round. If we want to know whether two vectors are parallel, all we have to do is show that one of them is a scalar multiple of the other. We can multiply and divide by a negative number. And again, we would multiply or divide each component. So, if we have minus 3 times minus 2, 3, we would get, for the I component, minus 3 times minus 2 is 6, and for the j, minus 3 times 3 is minus 9. And in component form, that would look like that. Or if we divide, we'd have minus 2 divided by minus 3, which would give us 2/3 for the I component, and 3 divided by minus 3 is minus 1 for the j. And again, we can write that in ij form. And what does it look like? Well, what we can see is that the multiply by minus 3 version is 3 times as long, but in the opposite direction. And that makes sense because the 3 makes it 3 times as long and the minus makes the direction opposite. So this time we note that the direction is reversed and the vector is stretched. For the a divided by 3, then it is 1/3 as long, or the length is divided by 3 and the direction is reversed. So direction reversed and vector contracted. And just to reiterate, we don't have to draw our result from the same point, so this would be an equally good representation of the division of a by minus 3, and we can see that we've drawn the green A divided by -3 vector off to the side there. It's also worth noting that obviously, because we're dealing with a screen which is two-dimensional, all our examples look like they're in 2 dimensions, but they work also in 3 dimensions, which, as I've mentioned, you will come across later.